Software Engineering Radio, Episode 56, Sensor Networks. Welcome everybody to this new episode of Software Engineering Radio. This time we're going to talk about sensor networks with Steffen Schaefer. And before we delve into the topic, I think you should probably introduce yourself and tell our listeners what you're doing and who you are, where you come from, and all that stuff.
Thank you, Marcus. I've been with IBM actually since more than 10 years. I'm an architect. My task is to deliver solutions to customers. I've been working in the wireless space for more than 6 or 7 years, starting from mobile phones. Then I did a few projects in architecture around RFID, and for the past 2 or 3 years or so, I've been working on a solution around container tracking and got a deep expertise in sensor networks.
So this is going to be the kind of case study we're going to talk about today, tracking containers. So why is container tracking important? Container, if people think of containers, this is more like a mechanical problem, big cranes, trucks, ships, but it seems like there's a lot of intelligence behind that.
Okay, yeah, that's true. So first of all, I think we should look at this as an example for a sensor network solution. So a lot of the lessons that we've learned in this application, you can translate really into completely different areas. Now, container tracking is interesting out of various reasons. First of all, there are two main problems. One is there's a real threat for containers to be misused, to be, for example, used to carry dirty bombs or to smuggle drugs or human beings or other unlawful material. So that is the perspective that, say, a Homeland Security organization might have to secure the country and improve the level of security. The other aspect is really the supply chain optimization aspect, where people want to get a better view of where their goods are, have they been shipped at the right temperature level, and so forth.
So before we go into the details, to give our listeners some kind of impression about how big this problem is, can you give us some numbers? I mean, how many containers are there per year, or how many of those fall off the ships? I don't know. So do you have any numbers?
It's an excellent question, and let me start with some anecdotal maybe.
Yeah.
A few years back, I moved house from New Zealand back to Germany, and I've been waiting for my for my belongings to arrive, to be shipped from by a container for, you wouldn't believe it, for 6 months. And for a little while, I mean, I was expecting that it wouldn't take so quick. And they, when they loaded everything in the container in New Zealand, they told me it would take around 6 to 8 weeks. I rang them after that time, and I first got the answer that the ship was delayed due to bad weather and those kind of things. But after a couple of months, those guys at the transportation company really ran out of explanations, and they frankly admitted then at some stage that they had no idea where my container was. Yeah. Eventually it showed up 6 months later, and I got everything, but it looked to me like more or less accidental. Yeah. Now, coming to your original questions, so let's look at a few numbers, how many containers there are. And so you need to understand that 90% of all goods we deal with are forwarded at some stage in ocean-going containers. So basically everything we use has been at a container at some stage. There are 20 to 25 million containers in the world that go on 4 to 5 trips each year. So there are close to 100 million container trips.
Yeah.
And there are only 2 to 4% of the containers that get inspected.
And how many fall off the ship?
I think that's one of the big unknowns, but it does happen.
Yeah.
It does happen. And looking at how world trade is increasing, and especially China becoming the production hall of the world, it is clear that container traffic will increase in the next years. And the alternative is not to make this more secure. The alternative cannot be to increase the number of inspections, say, but you need to come up with a smarter way on controlling what's going on out there.
And one way could, for example, be that you define some kind of area in which the container is legally to be used, right? So kind of transport corridor, and if it goes out this corridor, there's some kind of alarm raised. Would that be some kind of application for the things we're going to talk about?
Yes, exactly. A very good use case, and that's one of the things that we implement with our solution here.
Right. Okay, so then let's look at the solution a little bit and technical challenges that are involved in there. So I guess if you want to track containers, there is probably some kind of device on the container.
Exactly, yeah. So you can do it with different technology, and some people use RFID tags on containers, and that makes sense as long as you're clear. You can only get visibility of this container as long as it's at a place where you have RFID readers.
Like, for example, in the port or something.
Exactly. So that might be the case in container terminals. So you could roll out RFID readers to all container terminals in the world. And if the container happens to come by, it sends information that it's still, it hasn't been tampered with, and we know where it is. However, those container terminals and the places where you could roll out RFID readers, those are typically the more secure places during the trip. Yeah. And the dark places when that might be crossed when the container is on a train or on a truck are not taken into account. So that's why we believe you need to come up with a device and technology that not only uses short-range radio like RFID, but also that you have wide-range radio, hopefully with global coverage, to send real-time alerts, so that at the moment when a container gets tampered with, for example, there's a door open incident, you get a message, a notification in almost real time about this incident.
And we're going to talk about the specific technologies of this stuff later, right?
Yeah, absolutely.
So the typical components are then probably some kind of device, I think it's called TREC or something, on the container, and it communicates via satellite or?
What we have done at IBM is we have developed a tamper-resistant embedded controller, as we call it, or short
that's
TREC, the TREC device. And it's a device that sits at a container door. It has a number of sensors built in. It has microprocessors. It's got a clock and GPS. It's got a smart card also to really secure the data that's being collected. And it has a number of wireless communication features. It supports several wireless protocols, some short range, some wide range, to ensure that we really can send out a message in almost real time.
And what kind of performance do we talk about in the processor? Is it like, probably not, is it a Pentium with 10 gigs of memory? What kind of scale of processor do we talk?
Yeah, for sure not. I mean, those are low power processors. Think of processors you might find in a mobile phone or below. We use use low power processors, and a couple of them. We have one that is a bit more powerful, and that does the communication. And we have another one another one that does the computation, the filtering, and the processing of the information that is coming from the sensors. And the idea is obviously to switch off the main processor for most of the time,
right,
just to preserve and save energy.
Yeah. So then you have probably a number. So where do you get the power from, actually? Is there a big battery, or how does this work? Solar panels?
No. We thought about solar panels, but it's not really a good. It's not very suitable, because containers for most of the time would be stacked under on the vessel and wouldn't see daylight or wouldn't see the sun. So we do use a battery, a fairly powerful battery. With a lifetime, we think of our application of 2 to 3 years.
Oh, okay. Mm-hmm. And what kind of sensors does it have? I mean, the point is to monitor the container to make sure nobody opens the door or it's not getting too warm if it carries temperature-sensitive goods. So what kind of sensors does it have?
It's got a whole range of sensors, and I'm currently not allowed to talk about all of them. But let's say there are sensors that detect door opening. We detect mounting. If this device is mounted on a container door, we can determine temperature, the humidity. We can determine also light. Is there light inside the container? Which might give us indication if, for example, someone has drilled a hole, if that comes unexpectedly.
Right.
Or we can also check for acceleration to know at the end of a trip if a container, or whenever it happens, that if a container has been dropped, and those sort of things. If you like to think of GPS as a sensor, that's a very important piece for us,
then, basically.
To determine where in the world are we, where is the container.
Yeah, I guess. I mean, if I look at this, there is this central processor at some time, at some place, and then you probably have the kind of a network around the container where you connect these devices that are located at different positions on the container. So is it a kind of networked system, or are all the sensors mounted in the device itself?
Right now, the sensors are all contained in the device, but we have designed the solution flexible enough so we could also connect to external sensors. So those could be inside the container or even outside the container.
Mm-hmm. Okay, now let's look at some of the mostly backend and software infrastructure. After all, we are software engineering radio and not hardware and container shipping information services. So let's look at the backend a little bit. What kind of software and backend components are involved in that? So maybe first of all, before we talk about the backend, what kind of, is it Java? No, you're not Sun. So is Java running on the TREC, or is it native code, or what's running there?
No, it's not. It's not Java, certainly. With the power constraints I was talking about, you need to. It's just impossible to run Java or any kind of, say, a decent middleware on that. We use C for implementing the application on the track, the applications there. And then we use Java for all the rest of the solution. So, for example, we have also a handheld that's part of the solution. There we use Java. We use Java on the backend, of course.
Okay. So, what backend components are there in this whole infrastructure of this thing?
Okay. Well, the backend actually plays a very important role here. It does various things. First of all, the TREC needs to be configured for every single trip. So we have, with every container shipment, we have a unique, almost unique combination of things we need to watch out for. So, for example, the temperature range could be dependent on the commodity we ship, the geofences that we create are directly dependent on the root, obviously. So on the backend, first of all, you need to configure all those parameters that you want to watch out for, and then download those things on the TREC device. To stress on what we have mentioned before on the power constraints. The overall principle. There are some overall principles that you need to consider when working with scarce resources where battery power is very precious. When you want to achieve a battery lifetime of 2 to 3 years, you need to look at the following things. Let's say you need to do most of the computing, or you need to do some computing on the device to minimize communication.
Right. Probably expensive if you do it via satellites.
Yes, or if you communicate, unless if you don't have to, you're wasting energy. Imagine not charging your laptop or your mobile phone or your PDA for 2 or 3 years. That would never work, right? So you would you use a number of strategies to implement those things. One is, as I mentioned before, switch down the TREC device whenever you can, or the switch off the major processor. The other is only talk when you have to. Think twice before you speak.
And that is why you download all those boundary parameters down, so it's not going to report stuff all the time and you track at the backend, but rather you only report if something is wrong.
Exactly. So this is why I come to speak on this. So this is why this configuration on the backend is so important, that you really can be precise what events you want to be notified about. So so that is one thing. Now getting back to the backend configuration. The other is then that we have a TREC gateway, which is a hosted service we provide at IBM. So all the TRECs that are sending messages from all over the world send the messages to the TREC gateway, so we can then catch those wide range messages and forward it to the owner of this data. For example, a shipping company or a shipper. To send it directly then into their environment. What you need to do though is really simple. You mount a TREC basically on your container. You specify the rules through a user interface, and then you can sit and watch the MQ messages coming into your network.
Okay.
There are a couple of other important components in our backend. Let me just touch on the EPC network, a networked database where we tie information from various parties together. It's not really a sensor network issue, but if you want to integrate RFID technology, which is extremely important for transportation industry and retail, you need to have this kind of integration. And then we have we have a few more components about. I think we don't need to talk now.
Okay, so let's talk a bit about the details of the communication of the TREC device with the backend. We already mentioned that there is maybe satellite communication if you're somewhere on the water, so on the ship.
That's right. Yes. We have 3 ways to communicate from the TREC. Let me start with the short-range radio.
What do you need short-range radio for? Where would you use it? Before we talk about the technical details, what's the use case?
Okay, this is, for example, for someone going close to the container using a handheld device.
Okay.
Or then we do want to allow for local networks similar to RFID. We just want to make it as an optional feature and not as a mandatory feature. So if someone wants to roll out wireless routers that communicate over short-range radio to our TREC device, if they want to set it up in a container terminal, that is possible indeed.
Okay.
And so this is what we use the short-range radio for, and to make it extremely power efficient and to use a protocol that really has been optimized for this purpose. We use Zigbee, which has been developed for, optimized for very low power consumption. It doesn't have the greatest data rates, but it's enough.
How fast is it? Modem speed or?
No, it's 20. Starts from 20 kilobit per second to 250 kilobit per second, and reach is also relatively limited. Could be up to, say, between 50 to 70 or 100 meters, depending on how much you power it up.
Right.
But we think it's just the right thing for us, and other short-range protocols like Bluetooth we believe are not quite as suitable because they take too much energy.
Okay.
The other interesting thing is that we can use ad hoc networking capabilities that are built into the protocol, meaning that mesh networks can be built to have each of the tracks communicating, acting as routers and transmitting signals onto a network coordinator that is installed, say, somewhere in a terminal.
So are you saying that these devices dynamically find each other, kind of, and then some play the role of a coordinator or a hub, and the messages are passed on from device to device to device? So you have more than 100 meters in some?
Exactly.
Cool.
That's the idea of an ad hoc network.
Okay.
Yes,
I mean, I know the term ad hoc network more in the terms of dynamically discovering what's there.
Right. Okay.
And not necessarily that they coordinate the interactions in order to get an even bigger overall reach.
Okay.
So,
yes. Yeah. And you're right there. But here with Zigbee, we can also build mesh network where then the containers can, or that the Zigbee transceivers can chain up and relay the communication.
And the protocol that's run is probably not IP or something. That's something proprietary.
We are currently working. Yes, we are currently working to get some higher level protocol on this. It's currently not available out of the box, so there's still, I would say, some toothing problems, and there are issues around compatibility of stacks, and so it's not quite as smooth, by far not as smooth as when using other more established protocols.
Right, such as
Bluetooth, for example, where it's relatively, which is of course nowadays relatively standard and relatively straightforward to hook up devices and so. And with Zigbee at this stage, quite honestly, you need to do a lot of basic development still.
Okay, and Zigbee is some kind of industry standard or IBM proprietary? Or?
Absolutely not. We want to use open standards wherever we can, and Zigbee has been defined by the Zigbee Alliance, which today has, I think, more than 100 companies behind it.
Oh, okay.
And it's an emerging standard that is used in a lot of applications, for example, around smart home.
Right.
Think of a smoke detector that you build in your studio, and you don't want to check or replace the battery every few weeks. So it's really developed for devices
very low power
with a battery lifetime of several years.
Okay, so that was the low-end extreme communication thing. The other one is probably like worldwide communication through satellites.
Yeah, exactly. So, and there's something in between actually. So, when we try and send any data from the TREC, we look first for a Zigbee network, because then communication comes for free. If we can't
free in power or free in money, both probably almost.
Okay, well, it's low in power
and free in money.
Once you have rolled out the routers, it's zero in additional cost, right? Or almost zero. But then, if we can't find a Zigbee network close by, we escalate and we look for a GSM network.
Right.
So then we use, if we have that, we use SMS or GPS connectivity using the GSM. And if we also can't find a GSM network, if you're at a really remote place, we use satellite technology.
Okay, so there is. I mean, I know these satellite phones. You know, the reporters in Iraq with these big satellites phone during the war. Everybody has seen those. So, but you probably don't have this big antenna anywhere. So how does this work? I mean, are these geosynchronous satellites or is it LEO stuff? So I didn't know that this is possible from such a device.
It's a very interesting point you're bringing up there, and actually satellite communication has changed quite dramatically over the last year or so. Starting from this usage as a voice communication, we today have. It's more and more used for data communication, and while you can use it for kind of for broadband communication since a while, this has not been really useful for us. It's not what we need it for. So what has happened in the in the last year or so is that the modems got shrunk in size, also got cheaper. And there are specialized data services that are now provided by satellite providers.
Okay.
And that is very similar to, say, a text message to an SMS message that you can use today, and also becomes fairly reasonable in price.
So how much roughly?
I don't know it from the top of my head, but you can say fairly competitive to SMS messages.
Cool.
Yeah. What you need to consider, though, is that there's a big difference between the various satellite providers and technologies. Yeah. So there are, for example, geostationary satellites.
Yeah, but you probably need more power because they're further away.
Exactly, and that is the reason why. So that is one issue that why we're not using this kind of technology. First of all, it takes more power because the signal needs to travel much further. Yeah. Actually, it's 36,000 kilometers away from the Earth, and that takes up more power than with other systems.
Right.
The other point is that you need to point your antenna towards the south. Or towards the equator, wherever you are in what hemisphere. And that, of course, is not possible for in a sensor network environment like where we are.
Yeah.
So what we use instead is low Earth orbit satellites, and they only circle in 600 to 1,600 kilometers distance above the Earth, above the surface. And that means that we can set up connections much quicker. We need not as much power. We don't need to direct the antenna because that kind of system uses many satellites. So maybe say 80 satellites, some 80 satellites in the case of Iridium, and then you have basically reach to any of the satellites at any point in time.
most of the listeners probably know that we at Software Engineering Radio, and probably I personally, have some kind of bias towards talking about middleware and infrastructure and architecture. So what kind of middleware solutions are available? Is there like broker, CORBOP broker, maybe, I don't know, sitting on the device, or some messaging service, or what kind of infrastructures are used there?
Well, not on the kind of devices we're talking about. I mean,
they're too small for this infrastructure.
Yes, absolutely.
Okay.
You would find some kind of infrastructure, or if you're lucky, a JVM on say academical devices. Say the sunspots that have been presented recently. They have a JVM on them, and I would look at them as multi-purpose devices for academical experiments, and that's great, for those kind of things to implement and various applications on those devices. So you want to research
different algorithms, how these things coordinate and stuff, but you say it's not suitable for power sensitive real world applications.
Exactly. And when you look at then, for example, a real application where you are power constrained, where you're cost constrained, and you need to roll out thousands and tens of thousands, maybe hundreds of thousands of devices, you need to be very careful about the cost and the power, of course, as we mentioned before. And so let's say this a Java virtual machine or any decent middleware is quite a luxury on those kind of devices, and I'm not sure how realistic it'll be for the next 2 years or so to emerge. Still, we want to and we need to integrate the communication, the messages that come from those kind of devices with backend infrastructure that's in place today. So the easiest way to do this is really to kind of enhance your enterprise service bus on those devices, so you get messaging into the real world. And the
http://mycontainer.com or something.
Kind of. I mean, our way to do is, and I think this is it's quite widely accepted. I mean, you do this with messaging, right? You need to have asynchronous messaging here, and our products here are widely accepted on the backend. MQ series is, I think, by far the most often, most commonly used messaging system. And what we've done in the past years is that we extended that platform onto other devices. So, for example, we have a microbroker that runs on handheld devices, say, or it could run on hardware appliances. Wherever you have a Java virtual machine available, you can run this, say, in an J2EE, in a J2SE, in a J2ME, OSGI environment. Exactly. It's a relatively small client, 250 kilobyte of Java code, and there you go and do messaging to the big iron. If you want to go one step further, though, and you haven't got a JVM available, you can use a protocol that we call MQTT. It's an open protocol. If people are interested, you can look this up on mqtt.org, mqtt.org.
And we'll put this into the show notes, this URL.
Okay, great. And it's here the idea is that you have a native client that could be implemented in C or Java or whatever you have on your device. It can be as small as 30 kilobyte, and it has then a defined set. It uses this defined protocol to communicate to the backend.
What does the TT stand for? Is it time triggered, as in TT can, or is this different?
The TT stands for telemetry transport.
Okay. Okay, I thought I'd ask. So I've heard this term, the Internet of Things, a couple of times. That's probably the reason why we have IPv6. If every thing has its own IP address. So how does this stuff we talked about already, this TREC and this communication stuff and this worldwide thing, how does this tie into enterprise and applications? What's the bigger picture that we're talking about?
Okay, well, when what I think of the Internet of Things is not so much related to IP, or it does not mean that every object would have an IP address. It is more that you tag objects you're interested in, and by using an RFID tag, say, or in most cases. So you give it an identifier, a radio frequency identifier, to then relate information that is stored on the backend with that particular object.
Okay.
So let me give you an example. You have, say, a pharmaceutical product, a box of, or a bottle of medicine, and it is something very, very important. Could be life threatening or whatever if you use it in wrong doses or if you use the wrong one. And so let's use this as an example. And you want to track this bottle of medicine on an item level. So what you could then you give this an identifier. What you keep track of is things like when has it been produced, where has it been produced. This is information that the manufacturer knows. Yeah. Then there's a transportation process from the factory to some hospital, say, and the transportation company in this case would know the transportation conditions of this product during the shipment, and say for pharmaceuticals the temperature range might be interesting, and you want to record the fact, has it always been in the right temperature range, and then when you have it in the hospital, you have other things that you want to record, like has it been stored at the right temperature? Do you need to recall it, and so forth? And this is what we think of the Internet of Things, or what other people think of the Internet of Things, of objects. And
so it's not about the intelligent refrigerator that runs its own web server, but rather the idea is to identify things with a unique ID and then store its complete lifecycle data on different backend systems.
Exactly.
Okay.
And then coupled with a lot of concepts that you see in the Internet today, meaning that there cannot be, for the kind of data we spoke about, there cannot be one single central database
Got it.
containing all data. So what you do instead is you have a distributed set of databases, like each company has their own application server and web server, and serves their pages and serves their applications. But you need to have a little bit of central infrastructure, similar to a domain name service that points you, that takes you to the right IP address. Once given you have a URL, that you end up at the right IP address and the right server serving you the pages you're interested in.
Right. So there is the central thing that basically knows which of the participating backend systems have dealt with a certain RFID identifier number thing.
Exactly. So the idea here is of the Internet of Things that's being defined by EPC Global.
What does EPC stand for?
Okay, I should have mentioned that before.
Product code, right?
Electronic Product Code is really what EPC stands for. So it's the successor of barcodes, I feel like.
Okay.
And with the difference that barcodes act on a class level. So basically the barcodes of all bottles of Coke would be the same. But now with the electronic product code, you can differentiate the various Coke bottles.
Every Coke bottle has its own unique personality.
Exactly. Now, this might not come true with Coke bottles in the near future, probably. But I think it will come true with some of the pharmaceutical products.
Yeah,
and that's why I gave this example before.
Yeah.
All right, but the idea then with that EPC Global is driving here is that this network of EPCs is set up, and that each company has their EPCIS, their EPC information service through which they serve data, make that data available to other parties, typically using a web services interface. To find that data, you use a discovery service that works somewhat similar to the DNS in the internet. So you would know where you would find information about a particular item, given you have an EPC code or given you have other information, and that discovery service together with some other technology can traverse the EPC network for you and deliver you the right results. I think this is a very fascinating area that we are going to see emerging here, and there'll be queries that we can respond to that people cannot even think of today.
Okay, so anything else we forget to talk about? Anything else you want to leave our listeners with? Any pearls of wisdom that you want to get rid of at the end?
Well, let me think. We had a kind of interesting discussion at the UPSLA workshop here the other day.
So maybe just to mention, we're at UPSLA 2006 in Portland, Oregon, where we record this. Actually, we're both from Germany, but we still have to meet in America to do this recording.
Exactly. We meet once a year, roughly, which is at UPSLA.
Yeah.
But anyway, it's so we had this discussion yesterday about the staying in the Java paradigm, and it goes back to the argument I made before. I mean, we need to be clear that Java is not does not equal Java when you think of J2EE, J2SE, J2ME, Java on the sunspots. The language might have, it's the same name, but it's a different paradigm, and that's what one should be clear about when getting into, say, mobile device development or, getting into sensor networks. There's a huge importance, actually. We haven't spoken about this a lot. I see J2SE and J2ME very relevant in wireless routers or edge servers that, for example, coordinate a fixed installed set of sensors or RFID readers, and there you can run OSGI and so on. But again, what I want to point out is that the programming paradigm you need to apply to each of those devices is very different.
Okay, then Steffen, thanks very much for being on the show. I think this was fascinating, even if it wasn't just software and more like a systems point of view. Thanks.
Thank you, Marcus, for inviting me. It's been a pleasure.
Yeah, see you next year at UPSLA. Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.